Hi, I hope you're watching this after solving the problem. In part A of this problem, given is the circuit of a graph with 5 known current branches, as shown in blue in this picture. It is asked to find the 4 unknown current, I's of t, I's of x, I's of y, and I's of z. Simply writing KCL equations for node number 5 finds the I's of t as the arbitrary direction for I of t is shown here. I of t will be minus 13 amp. Same for other nodes. The KCLs at node 4, node 7, and node 2 and 3 will reside in the required current branches, I's of x, I's of y, and I's of z. You may deduce that the current at all the other 6 branches are gained by these equations. You notice that 5 known currents was enough to solve for all unknown current in this circuit graph. In part B, it gets more interesting. This is asking you how many independent known branch currents are enough to find all other unknown currents. Simply, you may count for the number of branches in this circuit graph, which is 11. The number of nodes in this graph is 7. Hence, number of independent KCL equations is 6. So, as the summation of all KCL equations reduces to 0 equals 0, hence they are not all independent. Therefore, number of independent current variables should be 11 minus 6 or 5, as we showed in part A. Okay. Now, part C asks you whether every 5 current branches are independent or not, by giving you 4 current branches as these red ones here, I's of x, I's of y, z, and t, and asking you to find the 5th independent current branch. As shown in these figures, out of all 6 other possible branches, only 4 of them gives you an independent branch. This one from 2 to 3, this one from between node 2 and 1, this one between node 1 and 4, and this one between node 3 and 4. For example, this one between node 6 and 1 does not give you independent current, because writing the KCL here, knowing the I's of z and I's of x, you know this current. So this is not an independent current equations. Okay. Part D is the dual of part C, asking you how many independent voltage variables are needed to find all other unknown voltages in the circuit. Again, there are 11 branches in this graph, so there are 22 current and voltages. Number of independent KCL equations is 6, and hence number of independent voltage equations will be 22 minus 11, which gives you the number of unknown voltages minus 6, which is the independent KCL equations. So there should be 5 independent voltage equations to give a unique solution to this problem. So the number of independent voltage variables out of all 11 should be 11 minus 5, which is 6. Hence, we need 6 independent voltage variables to find all other voltages in this circuit graph. Okay. And part E is the continuation of the previous part. We proved that number of independent voltage variables is 6. Here 5 is given, so at least one more independent voltage is needed. Okay. Again, part F is the continuation of previous part, asking you to determine which branch voltage is considered as the 6th independent voltage. Out of 5 branches that are left, these 3 ones, which I shown with green, can give you an extra independent voltage. This one between the branch between 1 and 6, the branch between 6 and 7, and the branch between 6 and 3. The others, the other 2 ones, will not give you an independent one. For example, if you consider this one between 2 and 7, you can write a KVL equations through the path that, for example, simple one. Consider one between 1 and 2. This does not give you an independent one because you write the KVL equations from 1 to 2. It gives you this voltage. So this voltage depends on the voltage of this branch plus this branch and plus this branch. Same for other 2 ones. Okay. The goal of this problem is to make sure you understand the number of known and unknowns for each graph, second graph. One note is that for this graph which I've shown here is not a planar graph. So maybe you have seen an equation between KVL equation and KCL equation does not validate for this particular circuit as it's not a planar. Okay. Hope